Google Cloud Machine Learning and Generative AI, how Agentic AI, modern ML frameworks, and the future of machine learning are reshaping business. Hello and welcome. Today we are diving into one of the most important shifts happening in technology right now, the convergence of Google Cloud Machine Learning, Generative AI, Agentic AI, modern model frameworks, and the future of machine learning. This is not just a story about better algorithms or faster chips. It is a story about how software is changing from fixed tools into systems that can understand language, create content, reason across data, and increasingly take action. Google Cloud sits at the center of this change because it combines infrastructure, data platforms, AI models, MLOps capabilities, and enterprise security in a way that helps organizations move from experimentation to real deployment. In this video, we will break down what these technologies are, how they fit together, what frameworks matter, where the opportunities are, and what the next phase of machine learning is likely to look like. To understand where we are going, it helps to remember where machine learning came from. Traditional machine learning usually meant training a model on structured data to predict a label, classify an event, detect fraud, forecast demand, or recommend a product. Teams worked with tabular data, feature engineering, model training pipelines, and deployment infrastructure. Success depended on data quality, experimentation discipline, and operational reliability. Google Cloud built many of its machine learning offerings to support exactly this journey, from data preparation and model training to deployment, monitoring, and governance. What has changed now is that machine learning is no longer limited to narrow prediction. With foundation models and large language models, AI can work across text, code, images, video, speech, and multimodal data, which makes the technology more general, more flexible, and much more visible to business users. Google Cloud's machine learning ecosystem is broad because enterprises do not all start from the same place. Some want fully managed services. Others need custom model development. Some are focused on classic ML use cases such as churn prediction or quality inspection. Others are now building co-pilots, search assistants, document intelligence, and AI agents. The platform has evolved to support all of these needs through services such as Vertex AI, BigQuery ML, data and analytics tooling, managed Kubernetes environments, TPUs, GPUs, model hosting, feature and metadata management, and integrated security and governance controls. The practical importance of this is that organizations can choose the right level of abstraction. A data scientist might fine-tune a model in Vertex AI, an analyst might build a predictive model in SQL with BigQuery ML, a developer might call a generative model API and add retrieval from enterprise data. That flexibility is one reason Google Cloud remains highly relevant in the AI platform market. Vertex AI is the centerpiece of Google Cloud's modern AI stack. It is designed as a unified platform for building, tuning, deploying, and monitoring machine learning and generative AI systems. In the earlier era of ML platforms, teams often had fragmented workflows with one tool for notebooks, another for training, another for deployment, and still another for monitoring. Vertex AI brings many of these capabilities together so organizations can standardize how models move from concept to production. For traditional ML, it supports training pipelines, model registry, experiment tracking, feature support, online and batch prediction, and model evaluation. For generative AI, it extends that workflow with foundation model access, prompt design, tuning options, evaluation workflows, grounding patterns, and application orchestration. The big strategic idea here is not just convenience. It is repeatability, governance, and scale. Generative AI changes the interface between humans and machines. Instead of requiring users to navigate menus, dashboards, or rigid workflows, generative AI allows interaction through natural language, images, audio, and conversational instructions. On Google Cloud, this has been strongly associated with the Gemini family of models and related tooling for building enterprise applications. Generative AI can summarize documents, draft content, generate code, answer questions, extract structured information, transform data, and help users interact with complex systems. But the enterprise challenge is not simply generating text. It is making outputs relevant, accurate, safe, and useful in business context. That is why generative AI in the cloud increasingly depends on retrieval, grounding, policy controls, evaluation, and observability. A model that sounds confident but cannot reliably connect to trusted enterprise data is not enough for production. This is where retrieval and grounding become essential. A foundation model is trained on broad public and licensed data, but an enterprise needs it to reason over company policies, product catalogs, engineering documentation, support tickets, contracts, medical records, or operational metrics. Google Cloud addresses this by combining model capabilities with data infrastructure such as BigQuery, vector search patterns, document processing, and application-level orchestration. In practice, this means a user can ask a question in natural language, the system can retrieve the most relevant internal documents or records, and the model can generate a response that is anchored to that evidence. This reduces hallucination risk and makes the output more actionable. It also creates a path from general intelligence to domain intelligence, which is the difference between a clever demo and a useful enterprise system. Agentic AI is the next major step. Generative AI can create responses, but agentic AI is about systems that can plan, choose tools, interact with software, maintain context over multiple steps, and pursue goals with some level of autonomy. The key shift is from generation to action. In an agentic workflow, a user may ask for a market analysis, a service case resolution, a software deployment check, or a procurement summary. The AI system does not only answer in text. It may search internal knowledge bases, call APIs, query databases, generate structured outputs, route tasks, ask clarifying questions, or trigger downstream processes. Google Cloud is relevant here because building agents requires more than a language model. It requires identity, access control, orchestration, memory patterns, tool integration, monitoring, and often event-driven architectures that can support reliable execution inside business systems. There is also an important distinction between simple agents and enterprise-grade agents. A simple agent can use a few tools and follow a narrow chain of steps. An enterprise-grade agent has to work under real constraints. It must handle permissions correctly, it must respect data residency and policy rules, it must log actions for audit, it must manage failures gracefully, it must be measurable, it must connect to systems of record without exposing sensitive data. This is where cloud platforms matter more than model demos. Google Cloud offers components across identity, networking, observability, data services, and application integration that help organizations build agents that are not just smart, but controllable. In the future, the winning AI systems will not only generate the most elegant output, they will be the ones that combine reasoning with dependable enterprise execution. Now let us talk about ML model frameworks, because these remain foundational even in the era of large models. TensorFlow has deep historical ties to Google and remains important for production machine learning, particularly in scenarios that require scalable model training, deployment portability, and mature tooling. Keras, now broader in its back-end support, has long provided a high-level developer experience for neural network construction. PyTorch has become extremely influential across research and production because of its flexibility, strong community adoption, and dominance in many modern deep learning workflows. JAX has also become increasingly important, especially in high-performance numerical computing and research settings involving large-scale transformations and accelerators. Beyond these, the ecosystem includes frameworks and toolkits such as XGBoost for gradient boosting, scikit-learn for classical machine learning, Ray for distributed execution patterns, and Hugging Face tooling for model and dataset workflows. The modern enterprise reality is hybrid. Teams often use multiple frameworks depending on use case, model type, and operational requirements. On Google Cloud, framework choice is less about vendor lock-in and more about workload fit. A team training a deep learning vision model may choose PyTorch. A team productionizing recommendation systems may use TensorFlow or custom pipelines. A team doing classical business prediction may rely on BigQuery ML or scikit-learn-based workflows. A research group exploring advanced transformer architectures may use JAX. Google Cloud's infrastructure and managed services are valuable because they support this diversity rather than forcing one framework on everyone. This matters because machine learning maturity is not about picking a fashionable library. It is about aligning frameworks, hardware, data pipelines, and governance practices with business outcomes. In other words, the best stack is the one that helps teams move from prototype to repeatable impact without unnecessary complexity. Hardware is another major part of this story. Machine learning at scale depends on accelerators, and Google has long invested in tensor processing units, or TPUs, as well as support for GPU-based workloads. Training and serving large models requires substantial compute, memory bandwidth, networking performance, and cost discipline. Enterprises are increasingly sensitive to this because generative AI can become expensive very quickly, especially when inference volume grows across customer-facing applications. Google Cloud's value proposition includes not just access to models, but access to infrastructure that is optimized for large-scale machine learning. That includes accelerator choices, managed training environments, scalable serving, and increasingly techniques for model optimization, quantization, batching, and efficient inference. Over time, one of the most important competitive factors in AI will be whether organizations can deliver strong model performance at an economically sustainable cost. Another key trend is the convergence of data engineering, analytics, and machine learning. In the past, data warehouses, data science environments, and application development often lived in separate worlds. That separation slowed delivery. Today, AI systems work best when structured analytics data, unstructured enterprise content, event streams, and model outputs can move through a common operational fabric. Google Cloud has pushed strongly in this direction by linking platforms such as BigQuery with AI and ML capabilities. This matters because many business problems are not purely generative and not purely predictive. A retailer may forecast demand, generate personalized content, summarize supplier issues, and automate service responses all within one business process. The future of ML belongs to platforms that can handle this mixed workload reality rather than treating analytics and AI as separate domains. We also need to talk about MLOps and LLMOps. It is easy to underestimate how much operational discipline matters in AI. Many models fail in production not because the algorithm is weak, but because there is poor version control, weak monitoring, unclear ownership, bad evaluation design, data drift, or no process for rollback and review. In the generative AI era, those concerns become even more serious because outputs can be open-ended and context-sensitive. Google Cloud's platforms emphasize lifecycle management, model registry patterns, monitoring, evaluation, and deployment controls. For generative applications, teams also need prompt versioning, safety testing, grounding checks, latency tracking, and human review loops where appropriate. The deeper lesson is that AI is now software plus data plus operations plus governance. Organizations that treat AI as a one-time model build will struggle. Organizations that treat it as an engineered system will be much more successful. Responsible AI has moved from a discussion topic to an operational requirement. This includes fairness, privacy, explainability where applicable, content safety, robustness, and governance over how models are used. In regulated sectors such as healthcare, financial services, public sector, and critical infrastructure, these concerns are not optional. Even outside regulated industries, brand risk and legal risk are significant when AI systems produce harmful or misleading outputs. Google Cloud's enterprise positioning has included strong focus on governance, security, and controlled deployment patterns. But the platform alone does not solve responsible AI. Organizations still need internal policies, risk assessments, testing frameworks, human oversight, and clear boundaries around acceptable use. The future of machine learning will be shaped not only by what is technically possible, but by what can be deployed responsibly and trusted by users, customers, regulators, and boards. Let us look at real use cases because that is where the technology becomes tangible. In customer service, Google Cloud-based AI systems can classify incoming requests, retrieve knowledge, summarize history, draft responses, and assist human agents. In software engineering, generative models can help write code, explain errors, generate tests, and improve developer productivity. In healthcare and life sciences, AI can support document understanding, imaging workflows, knowledge retrieval, and administrative efficiency, though high-risk uses require strict controls and domain validation. In manufacturing, ML and AI can improve predictive maintenance, visual inspection, planning, and supply chain resilience. In finance, they can support fraud detection, document processing, risk analysis, and internal knowledge automation. Across industries, the pattern is the same. The highest value often comes not from replacing people, but from compressing time, expanding access to expertise, and automating repetitive cognitive work. So what does the future of machine learning look like from here? First, machine learning will become more multimodal. Systems will not just process text. They will combine text, image, video, audio, sensor data, and structured business data in one workflow. Second, AI will become more agentic, meaning more systems will be able to reason across tasks and act through tools and workflows rather than only respond with content. Third, models will become more embedded in everyday software, so users stop thinking about AI as a separate product and start experiencing it as a built-in capability. Fourth, the balance between large frontier models and smaller specialized models will become more pragmatic. Not every task needs the largest model. Many enterprise deployments will favor a portfolio approach that uses the right model for the right job. Fifth, open and proprietary ecosystems will continue to coexist. Some organizations will prefer managed proprietary models because they value simplicity, support, and integrated security. Others will adopt open models for cost control, customization, sovereignty, or transparency reasons. Google Cloud's future role may depend heavily on how well it supports both paths, giving enterprises flexibility while preserving operational consistency. Sixth, evaluation will become a competitive discipline. The companies that win with AI will not simply have access to models. They will have better ways to measure task success, business impact, safety behavior, user trust, and operational reliability. Seventh, data quality will matter even more. In the generative era, many people became excited about models, but the enduring differentiator for enterprises remains trusted proprietary data connected to well-designed workflows. There is also a workforce implication. The future of machine learning is not only about data scientists. It includes software engineers, platform teams, analysts, product managers, compliance leaders, and business operators. AI development is becoming more cross-functional because deploying useful systems requires orchestration across data, infrastructure, policy, product design, and domain knowledge. Tools on platforms like Google Cloud are lowering barriers for more people to participate, but that does not remove the need for expertise. Instead, it changes where expertise is applied. Less time may be spent manually building every model from scratch. More time may be spent on architecture, evaluation, grounding, security, and workflow integration. In that sense, the future of ML is both more accessible and more demanding. For organizations planning their next steps, the strategic question is no longer whether AI matters. It is how to build a portfolio that creates measurable value while controlling cost and risk. A practical roadmap often begins with a few high-value use cases, strong data foundations, and a platform strategy that avoids fragmented experimentation. Google Cloud can play a major role here when companies need one environment that supports predictive ML, generative AI, agentic workflows, and enterprise governance. But success will still depend on disciplined execution. The organizations that lead in this era will be the ones that connect models to business processes, evaluate outcomes carefully, keep humans in the loop where necessary, and design for trust from the beginning rather than treating it as an afterthought. As we close, the big picture is clear. Google Cloud Machine Learning is no longer just about model training in the traditional sense. It now spans the full spectrum from analytics and predictive models to generative AI applications and emerging agentic systems. ML model frameworks remain essential because they shape how ideas become working systems. Generative AI expands what machines can create. Agentic AI expands what they can do. And the future of machine learning will be defined by multimodal intelligence, workflow integration, operational discipline, responsible deployment, and economic efficiency. The real transformation is not that machines are becoming more impressive, it is that organizations now have the chance to redesign how knowledge work happens. Thank you for watching, and I hope this gave you a clear and useful view of where Google Cloud and the broader machine learning landscape are heading next.